So here is the Mathcad for the design of a beam splice in accordance with NZS 3404. And we've already derived the member forces from a separate analysis. The design philosophy that we're using says that the applied moment is resisted by the flange plates, the transverse shear is resisted by the web plates, and the axial force is divided equally between the web by the flange plates. So therefore we need to check the flange plate capacity in both tension and compression, the bolt shear, the bolt bearing, the flange capacity, and the web plate capacity. And as an aside, I didn't make up these design philosophies, by the way. These have come from the NZ Steel Construction Handbook. And so for their example connections, they do set out what the design philosophy is for each of the connections. So we put in our connection geometry, and we're using, again, a 200 PFC, and we're using M16 bolts of grade 8.8. We scroll down, we're using a 70 by 12 mil flange plate, and there are bolts on either side of the connection to make up the splice. The splice also has web plates, and those are going to be 170 by 6 mil thick, and there's two bolts on each side of the connection. So our material properties, again, we're using the same material for the section size as well as the plates, the flange plates and the web plates. If you have different grades, you need to separate these material properties. It just makes your calculation simpler if you use the same grade. So our applied loads from the analysis, once again, we check our minimum loads as taken from the code, clause 9.1.4, or clause 12 is subject to seismic loads. And we design for either the applied loads or the minimum loads. So we begin with a check on the flange plate resisting the bending. And it's the moment applied divided by the lever arm. And we can see that the stress in the plate is below the yield stress. So, okay. Check on the flange plate bolts. So the bolts have a shear capacity that we've seen before. We take the yield or the ultimate tensile strength of the bolt multiplied by the area multiplied by 0.26. There is a factor if you've got lapped connections. That's taken from the code. You've also got a web plate resisting the shear. So check the shear capacity of the web plate. So it's the shear area multiplied by the yield multiplied by 0.6. Multiply it by a strength reduction factor, and that gives you 115 shear capacity. Check the ply, the bearing of the ply, and again you're looking at the diameter of the bolt and multiplying by the thickness of the ply, the web plate ply, and by the strength of that web plate. Okay, and we find it's below the applied shear load. Check if we've got a slender web, in which case shear buckling might be a problem. So we calculate our alpha V value from clause 5.11.5. And with that, we find that our design applied shear is lower than the design capacity. Let's check on the web plate bolts themselves. We've got a shear capacity in the bolts as derived similarly to how we derived above. And we have a design shear capacity of the bolt group of 129 kilonewtons. So again, we're okay.